A pleasant morning to one and all present here. Today we have our speaker, Dr. G. Lakshmi Narayanan, Professor, Head of the Department of Electronics and Communication Engineering, National Institute of Technology, Tiruchirappalli. Dr. G. Lakshmi Narayanan, an expert in high-performance digital VLSI architectures, VLSI-based wireless system design, physical layer design, and algorithm techniques for cognitive radio, VLSI signal processing, FPGA-based wireless transceivers, and reconfigurable systems. Dr. G. Lakshminarayanan received his PhD in VLSI systems in the year 2005. SAR has executed many research projects and fabricated chips through India Chip 2010 program under SMDP project. Dr. G. Lakshminarayanan has 20 years of experience in teaching and research. Dr. G. Lakshminarayanan has a patent and also filed 3 patents. Has published 26 international journals, 2 national journals, 51 international conferences, and 8 national conferences. Also, guided 6 research scholars. Currently, 10 research scholars are doing research under his guidance. Apart from this, Dr. G. Lakshminarayanan has national and international research collaboration as well. Also, received funds from various agencies. To his credit, he has executed 12 sponsored research and consultancy projects. Today, we have such an eminent personality to deliver a talk on pipelining and parallel processing. I welcome you, sir.
Okay, thank you to all. I will start my lecture. Thank you to all. So, good morning to all. Hello.
Good morning, sir.
Good morning. So now, 1 minute. Okay. So today, are you all seeing the screen? Hello.
Yes, sir. Visible. Visible.
Okay, visible. Okay. So today I am going to discuss with you the techniques used to improve either the speed or reduce the power. I am going to discuss. There are many techniques available. Today I am going to discuss pipelining and parallel processing. So I'm going to discuss pipelining and parallel processing. These 2 techniques which are used, how these 2 techniques are used to either increase the speed or reduce the power. I am going to discuss. And participants, I think if you have any doubts, see clear, you are allowed to interrupt. No need to wait at the end of the section, because I am taking lecture for you to understand. It has to reach every one of the participant. See clear? So it has to reach every one of you. That's why if you have any doubts, you are allowed to interact. See clear? You interrupt me and I am ready to explain till you understand. So these are the topics we are going to discuss today. Now let us see about pipelining. Okay. So pipelining and parallel processing. Pipelining, and we are going to consider the examples of FIR filter or understanding finite impulse response filter with that architecture, with that application, we are going to understand, is it clear, how to apply pipelining and parallel processing techniques. And pipelining is a technique. It is used to reduce the critical path of a circuit or module or a system. And do you know what is critical path? Anyone knows what is critical path? Why are we giving importance to critical path? Any idea? Anybody knows? Hello? Are you all are you able to hear what I am teaching? Hello? Are you able to hear?
Yes, sir, we can hear you, sir.
Okay. So critical path, see clear, if you consider any circuit or any system like filter, see clear, inside the module, so inside the system, you have multiple paths from input to output. There are multiple paths from input to output, and at what rate we allow to operate the circuit, what rate we allow to operate the filter is to be decided. That is decided by, so I told, in a circuit there are multiple paths available. You consider a path which is having longest delay. See clear, a path having longest delay is considered to be a critical path, and the delay of that path is, see clear, is deciding the operating frequency of the circuit or the system. Understanding? In, for example, in a circuit, if you have multiple paths with a varying delay of, I think 3 nanosecond, 4 nanosecond, 6 nanosecond, 7 nanosecond, 10 nanosecond, like that, from input to output. And here the a path, which path is having, I think, a path, a longest delay, the path having a period of 10 nanosecond, then that path is considered to be critical path. A path having longest delay from input to output is considered to be critical path. The delay of that critical path, the delay of that critical path is deciding the operating frequency of the circuit. So you can, if the critical path delay is 10 nanosecond, you able to operate the system at 10 nanosecond rate. Low, I think higher than 10 nanosecond period is okay. See clear, 11, 12, 13, anything is okay. But if you operate less than 10 nanosecond, 8 nanosecond, 6 nanosecond, like that, what will happen is you will not get a result. You are passing ith sample. See clear, ith sample, because of critical path, see clear, the resultant of ith sample, the worst case delay. Worst case delay of resultant of ith path reach the output will take 10 nanosecond. So you should allow 10 nanosecond, is it clear, for the data to travel to the output. See clear, if you give 10, more than 10 means no problem, it will be there. In a combinational circuit, unless you remove the input, resultant will be available at the output. That is the property of combinational circuit. The property of combinational circuit is that once you give the input, resultant of input after the specific delay available at the output. See clear, unless you remove the input, resultant is available at the output. If you keep more than 10 nanosecond, there won't be any problem at all. The result will be available. But if you operate that with less than 10 nanosecond, samples you are taking, ith sample, I plus 1th sample you are taking, the interval between samples I am saying. So if you take ith sample and you pump I plus 1th sample 10 nanosecond, that is after 10 nanosecond, no problem. If you pump earlier than that, then there will be a problem. See clear, resultant of ith data will not reach the output because before that you are pumping the next data. That's why minimum delay to be maintained, critical path delay to be maintained. That is nothing but the operating frequency. If it is 10 nanosecond, then the period frequency is 100 megahertz. To be able to operate the system at the rate of 100 megahertz, you are allowed to take samples at the rate of 100 megahertz. You cannot basically operate the system lesser than 100 megahertz. See, lesser than means you cannot operate them higher than that 100 megahertz. Sorry, because higher than 100 megahertz will reduce the time period. That's why you cannot operate. That is the critical path. So if I through pipelining technique, I able to reduce the critical path without changing the input output characteristics, because we are applying technique. Say clear, when we are applying technique, the condition should be we should not change the input output characteristics of the circuit. Say clear, of the submodule or system. Say clear, if you change, there is no meaning at all applying technique. If it is a filter, it has to work as a filter. See clear, when you apply pipelining technique, parallel technique, it has to work the same way. See clear, we are approaching because these are called frequency, area, power. These are called parameters, optimization parameters. So we are not changing the IO characteristics. We are, by applying techniques, we are working towards optimizing the parameters. Either we may reduce the area, we may reduce the power, or we may increase the speed. These are the purposes we are utilizing the techniques. And through pipelining, it is able to reduce the critical path. See clear, reduce the critical path. Indirectly, what we are obtaining, once we reduce the critical path, I able to increase the operating frequency. That's why you able to, by applying pipeline technique, we are reducing the critical path. So the technique is useful to increase the clock period, sample period. Either it may increase, it may give high speed. But if you don't want to increase the speed, then the technique you may use to reduce the power. How? I am going to explain. See clear. Then next technique is parallel processing. In parallel processing, we are not attempting to reduce the critical path. Instead of reducing the critical path, we are attempting to replicate the circuits depending upon the level of parallel processing. See clear, level means how many levels you are doing. If it is 2 level, that is represented by well-known letter L. See clear. So if L is equal to 3, 4, like that you may keep. Then threefold we are increasing the so threefold we are replicating the hardware. So by replicating the hardware, is it clear? We able to increase the frequency or we able to reduce the power. See clear? How? See clear? This is the advantages of these two techniques. How? Is it clear? The approaches I will explain in the following slide. Are you clear? Do you have any doubt? Okay. Now I am proceeding. Okay. I think concept I will explain now. See clear? And if you see the figure A, you see clear, figure A. See clear, what I am doing is, I am doing y of n is equal to x of n plus a of n plus b of n. See clear, 3 operands I am adding. And adder, every time it takes only 2 operands. That's why first I am adding x of n, h of n. Followed by the resultant, I am adding with b of n to get y of n. See clear? Or understanding? So x of n, a of n is, see clear, sample at nth instant. See clear? So it could be 8-bit, 16-bit, anything it could be. See clear? It is a word. And here if you see clear. Now what is the critical path delay from input output in terms of, you consider adder is having delay represented by t suffix a. See clear, t suffix a, otherwise you consider that is 5 nanosecond. Adder having a delay of 5 nanosecond you consider, so ta is equal to 5 nanosecond you consider. Now what is the speed I may able to operate this circuit? Any idea? What speed I may able to operate this circuit? 2 addition I supposed to do. According to figure A, I am asking. Any idea? Are you all attending? Okay, I will continue. Okay, here because I supposed to two addition, so each add is taking 5 nanosecond. Totally, I require 10 nanosecond. See clear? So the operating frequency of the system is 10 nanosecond. Now I want to increase the speed. See clear? How to do that? See clear? It is nothing but by pipelining, I able to reduce the speed. So by applying pipeline technique, what I am doing is that I am introducing to reduce the critical path delay. I am introducing pipeline latches in between. Wherever necessary, I am introducing pipeline latches. If you take figure B, the D is representing latch or flip-flop. See clear? So this is nothing but pipeline. By introducing registers is referred to as pipelining technique. And these registers are referred to as pipelined registers. See clear? Pipeline registers are pipeline latches. By introducing latches here, what advantage am I getting? Are you all clear? What advantage am I getting? Here, if you see, now you see the operation. Now I am giving x of n, a of n I am giving. Once I give x of n, a of n, அம்மாவோட செல் எங்க இருக்கு இல்லையா, அப்படியே இங்கேயே வெய்ய, நோண்ட இது பண்ண வேண்டாம், கிளாஸ் எடுக்கிறவங்க. Are you all clear? Hello.
Yeah, it's okay. Slide is showing now.
Okay. So, but have you all understood? I explained about pipelining. Any doubts? Okay, I will continue. See clear. So now let us see the idea of parallel processing. Parallel processing, what I am doing is I am replicating the circuit. If L is equal to 2, see clear. If L is equal to 2, I am duplicating the circuit. Class patrican solid. So if L is equal to 2, I am duplicating the circuit. If you see here, see clear. So this circuit, A circuit is duplicated here. See clear. Because L is equal to 2, it is duplicated here. Once I duplicate the circuit, see clear, I able to consider 2 samples at a time. See clear, I able to consider 2 samples at a time. So because of 2 setup I have here, if I consider, is it clear, even sample here, if I consider 0th sample here, first sample I may consider here. I need not again consider first sample here. See clear or understanding? That's why the single, previously it was single input, single output. Now I replicate the circuit, the system is changed to multi input, multi output. If L is equal to 2 means it is having 2 inputs, 2 outputs it is. So what I am doing is 0th sample I may consider here, first sample I may consider here. Then second sample I may consider, third sample. That's why odd, even sample you may consider here, all odd sample you may consider here. But every circuit is going to take 10 nanoseconds. See clear? But because of duplicated architecture, see clear, I am going within 10 nanoseconds, because 0th sample I am processing here, then I am in the same time, same 10 nanoseconds I am processing first sample here. See clear? By the way, within 10 nanoseconds I am getting 2 outputs. By the way, the effective sample period is reduced to 5 nanoseconds. For understanding? Because every 10 nanosecond I am getting 2 outputs. See clear? So the effective per sample, if you see, I am spending only 5 nanosecond delay. By the way, the operating speed is doubled. But here I have not introduced latches. Here I have replicated the circuit. Same circuit is replicated, by the way, speed is doubled. But area is increased, we will discuss. See clear? So these are the concepts of pipelining and parallel processing. Are you all clear? Are you all following? Following? Okay, I am continuing now. Let us move on to filter. See clear? Briefly, we discuss about how pipelining technique useful for increase the frequency of the filter. Let us see. So this is the, so now I have a filter, FIR filter. 3-tap FIR filter we are considering. So y of n is equal to a into x of n plus b into x of n minus 1 plus c into x of n minus 2. So it is a 3-tap. Is it clear? 3 samples at a time are used to get the output y of n. Okay. And the circuit for implementing this one is the circuit. This is the direct form 1 structure. See clear? So a is x of n is taken here. When this is x of n, what is available here? X of n minus 1, because after a delay I am taking. This registers introducing 1 sample delay. The registers are introducing one sample delay, x of n minus 1 here. When it is x of minus 1, what is here? In this tap, it is x of n minus 2. That's why 3 tap. First tap, second tap, third tap it is. So x of n minus 1, x of n minus 2. That is multiplied with the coefficient a, b, c, and I am getting the resultant y of n. Y of n is equal to a x of n plus b into x of n minus 1, c into x of n minus 2. Now you find out what is the critical path in this circuit. You take adder is having Tm delay, adder is having Ta delay, multiplier is having Tm delay. So what is the critical path today? What is the operating sample speed of the circuit? Operating frequency or sample speed of the circuit? So to identify a critical path, you need to look from input output. The path from input output you need to look. If it is a synchronous circuit, there are three places to be looked. Say clear? Because in synchronous circuit we are introducing registers inside. That's why registers as a storing element. That's why when you identify critical path in a synchronous circuit, in a combined circuit, it is between input and output. But in a synchronous circuit which is having registers, you need to find out the critical path. You need to find out the paths available between input and output, input and any one of the registers, and in 4 places between 2 registers inside the system, and output register to any one of the register inside to output. These 4 places you need to identify the paths. Again I am saying, if it is a synchronous circuit, in 4 places you need to identify the paths. The critical path available between either input to output, or it available between input and internal register, or it available between 2 internal registers inside, or between internal registers and output. In these 4 places you need to identify the paths. Among these things, which is having highest delay, that is the critical path. In this circuit, if you see, the highest path is this is the path from here to here. This is the highest path. Same way, this path also having this path also having equivalent delay. Same delay. So how many adders and multiplied with respect to components? We are saying the delay. So here one multiplier, 2 adders are involved in the critical path. Here if you see, here also one multiplier, 2 adders are involved in the path. Or you see, x of n through this one, through these 2 adders, y of n. This is one. Another path is this one. So clear, b, then this adder and this adder. So the critical path delay, say clear, the path delay is Tm plus 2 Ta. 1 Tm plus 2 adder delay. That's why Tm plus 2 delay. That's why the sample speed of the system supposed to be equal to or greater than this delay. The sample speed supposed to be the clock period. Sample speed is nothing but clock period. See clear? That is supposed to be greater than or equal to Tm plus 2e. The sample delay is 1 over the clock period. See clear? F sample is less than or equal to 1 divided by Tm plus 2te. See clear? And if you consider Tm is having 4 nanosecond, and the adders having 2 nanosecond. See clear? 2 nanosecond. Then the operating frequency is, see clear, operating clock period is 4 plus 2 into 2, because 2 adders in, so 8 nanosecond. The period is, the clock period is should be greater than or equal to 8 nanosecond, and the sample speed is, say clear, 1 by 8 nanosecond, 125 megahertz. You able to operate the circuit at the maximum of 125 megahertz. That is the general structure. Now I want to, say clear, reduce the delay. I want to increase the speed of the system. Now let us see how through pipe. Already we discussed the concept. Now let us see clear, how pipelining, using pipeline technique, how to improve the speed. Let us discuss. Oh. Okay. Now what I am doing is that, so in pipelining, I am introducing registers. I am introducing. So in order to cut the critical path delay, I am introducing registers. This here, if you see this structure, see clear. This structure, if you see here, only these two latches are there. Here, two latches are there. By pipelining, I am introducing additional latches. See clear? Here and here, I am introducing additional latches. See clear? By introducing these latches, now what is happening? See clear? Now what is the critical path delay? Is anyone can say? Now after introducing, I introduced latches. Here and here, I introduced pipeline latches. Now what is the critical path delay? Critical path delay is now it is reduced to, as I told, it is input to and this register, that's all. So it is, see clear, multiple delay and one adder delay. Multiplier delay, one adder delay. So the critical path is reduced to Tm plus T. It is not Tm plus 2Ta. So if we consider 4 nanosecond for multiplier, 2 nanosecond for adder, previously it was 8 nanosecond, now it has come to 6 nanosecond. See clear? So I think 1/4 improvement happened. See clear? So by introducing these two registers, the clock period is reduced. Clock period is reduced to 6 nanoseconds instead of 8 nanoseconds. And how? And by introducing these latches, now we are verifying that whether we have not changed the IO characteristics. We are verifying. Is it clear? So now we are checking. So with respect to clock, I am doing. With respect to clock, I am doing. So first 0th clock. Here I am pumping X0 sample. Here X of -1, and I introduce additional register here. That's why here itself, or understanding here itself, I will have X of -2, and see if I consider only 3 sample, for here I don't have anything here because the system is having X of n, X of n-1, X of n-2. X of n-2 is now here because into additional register. That's why here nothing is there. That's why, is it clear? In clock 0, I am taking X0. So here I am setting the node to know in which place I am doing. The node I am setting here 1, here 2, here 3, I am setting the node. Is it clear? Every clock cycle after pipelining, what I am getting in 1, 2, 3, I am going to discuss. Whether I am not violating the IO characteristics, I am discussing now. Is it clear? So if you see first here X0, see clear, I am starting with X of 0. Here X of 0 means here X of -1, here X of -2. 3 sample only. Here nothing is available. When I take X of 1 here, then here X of X of 0, X of -1, X of -2 is available. See clear? Because at a time, see clear, till X of -2 alone, I am, because it is 3 -2 alone, I am considering. See clear? That's why to node 1, if you see input, I am taking X0. And I understand that X of -1, -2 available in the circuit. Now if I take at node 1, what is happening? X0 I am taking, that is multiplied with A, and that is coming here. And here X of -1 is available, that is multiplied by B and available here. So at node, what I am getting? Resultant of A X of 0 plus B X of -1 I am getting. In node 2, what is happening? Because the result is first available here only. It has to go to at the first clock cycle I am checking. Go to here, I need one more clock cycle. That's why nothing is here. And here also no sample available in the first clock cycle. At 3, there is nothing is available. That's why I am putting dash dash, outputs also dash I am putting. In the second clock cycle, what I am doing? I am taking X of 1 here. When I take X of 1 here I will get X of 0, X of -1, X of -2, I will get here. So here if you see, here what I am doing at node 1, because it changed to X of 1. So A into X of 1 I am doing. Then here B into, see clear, B into X of 0, that I am adding here. And node 2, what I am getting? What was previously here in the first, what was here in the first clock cycle? See clear? The second clock cycle, that will come here. So first clock cycle, this was here at node 1. Now it has come to here, node 2, A X of 0 plus B X of 1, it has come here. And if you see x of minus 2, see clear, come here in the second clock cycle. That's why c into x of 2 I am doing. So at c node I am getting c into x of 2 I am getting. Then this whatever is here, a x of 0, b into x of minus 1, both things are here. Then the x of minus 2, the resultant I am, because it is pure combination. That's why the resultant I may get at y naught. So y naught, if you see what I am doing, a into x of 0 plus b into x of minus 1 plus c into x of minus 2 alone I am doing. So I have not changed the IO characteristic. Then for second sample also, next sample also I am verifying. So if you see second clock, first clock, second, third clock cycle, or 0th clock cycle, first clock, second clock cycle, I am taking x of 2. I am taking x of 2. See clear? So here I am doing a into x, x of 2. When it is x of 2, x of minus 1, x of 0, x of 1, x of 0, x of minus 1. So accordingly I am calculating here. So at 1, a x of 2, then b x of 1 is available. See clear? And the node 2, what is the previous clock cycle? What was the previous, that is available here. Then here minus 1 is available now. That's why c into minus 1 I am doing. So now y of 1 is nothing but, see clear, a into x of 1 plus b into x of 0 plus c into x of minus I am getting. So by introducing these latches, I have not changed the IO characteristics. Input output mapping I have not changed. But I reduce the delay to Tm plus 2 Ta instead of Tm plus 2 Ta. 8 nanosecond to 6 nanosecond I have reduced. So this way pipeline to be applied. And here I applied registers here. And in a general circuit, we need to know where to apply pipeline register. See clear? For that, clearly they told. See clear? Where to apply pipelining registers, they told. We will discuss. Okay. So the drawbacks of pipelining is used to increase the frequency. But the drawback is it increases the delay element. If you see the previous circuit, here one set of delay element, here another set of two additional set of delay elements I introduced. That's why that is the little bit area of overhead. And by introducing this one set of pipeline latches, this is one set of pipeline latches, it is going to increase the latency by 1. So here if you see in the second clock cycle only, instead of first getting the output first clock cycle, I am getting the output in second clock cycle. But that's why latency increased by 1. In the next clock cycle, I am going to get every output. It is initial delay. That's why it's called the latency. So then I am going to get the samples every output every clock cycle. See clear? That's why it is increasing the latency. See clear? And as I told, how to find out critical path. Critical path lies between sequential circuit. Critical path lies between input and latch and output, between two latches, or between input and outputs. It is available. It is available. See clear? And where to introduce pipeline register? I am explaining now. Pipeline latches can only be placed across the feed forward cut set of the graph. They told to introduce pipeline latches across the feed forward cut set of the graph. They told. Now we need to know what is feed forward cut set. Now let us see. First they are saying cut set. Cut set is a set of edges of a graph such that if these edges are removed from the graph become disjoint. See clear? For example, see clear? Each one is edge. This is the circuit. I may consider as a network also. See clear? When it is a circuit, this is called wired. Each one is wired. When I am considering this as graph, each interconnect wires are considered to be edges. See clear? This is one edge, this is another edge, like that. Okay. Then all of listen. Then these are the edges. I am going to introduce. If you see here, cut set. So once I remove some set of edges, the graph has to be disjoint. So if you see here, if I remove this edge and this edge, what will happen? There is no connection between input and output. Is it clear? Input output are disjoint. That's why I am not introducing latches only here. If I introduce latches only here, once I make a cut, in what are the edges? And another rule is, stay clear. A cut set is a feed forward cut set. The data moves in that I will tell you. So here I'm introducing pipeline latches only in the feed forward cut set. Is it clear? So here these these edges I have identified. Is it clear? If that is, you identify the edge, because our thought is to reduce the critical path. Unless you select edges which is available in the critical path, you cannot reduce the critical path. For understanding, that's why here this is the critical path. That's why this edges I have chosen, this wire I have chosen to make a cut. But once I make, then only there is a reduction critical path. Otherwise there won't be reduction critical path. That's why this I have chosen. And once I make a cut here itself, the graph will not become disjoint. But the rule is, once I make a cut, the graph has to be disjoint. That's why I compulsorily make a cut here also. So I make a vertical cut. I am making a vertical cut such a way that the graph becomes disjoint. Once I make this cut, two edges are coming in the cut set. This top edge as well as this bottom edge are coming in the cut set. That's why in these two edges, that is, pipelines are introduced in the feed forward. Feed forward means data is flowing only from input to output, not from output to input. In IR filter, data may follow from output to input, because FIR filter all are feed forward path only. That's why feed forward edges only here I am having, and I am making these two edges are cut. See clear? If I make two edges are cut, then only graph becomes disjoint. Then in those edges, what are the edges you cut? In those edges, our duty to introduce pipeline register. Once you follow this rule, the input output mapping is preserved. There is no violation on input output mapping. You need not, this is called a schedule. The bottom table is called a schedule. You need not again verify the schedule at all if you follow the rule. The rules are, see clear, you need to bring cut set. Once you bring, you need to cut set of edges. If you choose the edges supposed to be in the critical path, then only there is a reduction critical path. You don't cut only the edge available in the critical path. You choose set of edges. By the way, the graph has to become disjoint. Then in those edges, see clear, those edges introduce pipeline register. If two edges are there, in first edges, second edges, those edges you need to introduce pipeline register. Are understanding? By the way, in both edges I introduce pipeline registers. By the way, reduce the critical path. I have not violated input output relationship. By the way, circuit is operated higher speed. This is the way pipelining is applied in a, say clear, in a circuit. Say clear? Any doubts? Okay, I am proceeding. Now we move on to, say clear, the another one we move on. Say clear. This circuit all of you take. Say clear. This is, and previously what we saw is, this is direct form 1 representation. In the same way, three-tap filter can be represented in direct form 2. Three-tap filter. See clear? Three-tap filter. If you see here, this is direct form 2. Direct form 2 implementation of three-tap filter. And according to this circuit, what is the critical path delay? What is the critical path delay according to this circuit? Direct form 1 we saw. The critical path delay was Tm plus 2 Ta. Now according to the circuit, what is the critical path delay? Tm plus Ta is the critical path delay. That's why, see clear, when you want to, don't apply pipelining immediately. Is any other way to draw the structure, you analyze. If no way, then you pipeline. See clear? But here for concept only, we have taken direct form 1 and explained. See clear? With the direct form 2 also, but here also we may apply. For a given circuit, we are applying pipeline to improve the frequency, that's all. If this is the given circuit, you apply. For this, you apply. See clear? Now, for this one, how to apply, let us. Now, for this circuit, what they are saying is that the adder multiply is taking 10 nanosecond delay, adder is taking 2 nanosecond delay. By the way, what is this A? So the speed is 10 plus 2, 12 nanosecond. UT means unit of time, unit time delay we may say, but UT you may consider nanosecond. See clear? Order anything. See clear? So here, according to this circuit, the operating speed is 12 nanosecond. But I want to operate this one at 6 nanosecond. I want to double the speed. What to be uptime? Same pipelining. Previously, that was the circuit. We brought down to 8 to 6. Now, this is the circuit. Then you apply. Here, how to apply is that we go for, see clear, here the multiplier itself is taking 10 nanosecond. Now I want to get 6 nanosecond. A component available in the filter itself is taking 10 nanosecond, but I want to reduce the delay to lower than that. So what suppose do that? The multiplier is to be broken. See clear? Because always multiplier is having multiple stages. If it is 8 by 8 multiplier, it is having almost 8 stages. Every stage is used to generate one partial product. On a paper and pencil, if you do with 8 by 8 multiplication, 8 partial product to be generated. That is A0, B, A1, B, A2B till A7B, you need to generate. See clear? Then, see clear? Then you need to add all the partial products. See clear? Or understanding? And by the way, multiplier having different multiple stages. That's why multiplier can be broken. See clear? That's why I'm breaking the to get 6 nanosecond. I am breaking the multiplier such a way that, see clear, 6 plus 4 I am breaking. I am breaking to M1, M2. Multiplier M is 6 nanosecond, M2 is taking 4 nanosecond, followed by cut set. If I bringing the cut set in all these three edges, what will happen? Graph become disjoint. If I introduce only these two, graph will not become disjoint. If I introduce, is it clear? So introduce pipeline register here, 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 you introduce pipeline register. Once I introduce pipeline register, now what is the critical path delay? Either this one is the critical path or this one is the critical path. If here means it is having 6 nanosecond, if here means one multiplier plus one adder. Here also one multiplier, one adder. Together it is 6 nanosecond because I divided 6 plus 4. Because here adder delay with M2, adder delay is going to add. That's why I have divided 6 plus 4 instead of 5, 5. See clear? So 6, 4 I have divided plus 2 here added. By the way, the circuit will work. See clear? 6 nanosecond rate. See here also it is Tm plus Ta, but Tm is, sorry, it is not Tm, either it is operating a Tm1 delay or Tm2 plus Ta delay it is operating. Both are 6 nanosecond. Circuit may operate 6 nanosecond. And here we divide the components to bring down the delay. We divide the components to bring down delay. That's why this approach is called fine grain pipelining. This approach is called fine grain pipelining. See clear? Okay. Now let us move on to parallel process. How parallel processing used to increase the speed? Let us discuss. For understanding. Okay. In parallel processing, see clear? We are replicating the hardware. By the way, what is happening is, as I told, single input, single output system. SISO is converted into multi-input, multi-output. If I do 3-level parallel processing, I am going to replicate the circuit thrice. That's why I able to consider 3 inputs at a time. That's why 3 inputs I am considering, 3 outputs are getting. By the way, effective sample, everyone, X of 3, Y of 3, it is going to take same period. But effective sample delay. Here I am not altering the in pipelining, I have altered the clock period. See clear? Here I am not altering the clock period, but I replicated the circuit. By the way, per clock but I am getting 3 outputs. So effective delay is reduced by, sample speed is increased by thrice. See clear? And here instead of saying x of n plus 1, I am saying x of 3k plus 1 to indicate it is 3-level parallel processing. Here because of to indicate 3-level parallel processing, L is equal to 3. Here instead of n, it is represented by 3k. 3 for level, k is clock. See clear? So 3k plus 1, 3k plus n is replaced by 3k. That's all. So in parallel processing, because of replicating the hardware, single input, single output is replaced to multi-input, multi-output. Now let us see how to develop this circuit. Now let us see. See clear? Now this is here also I am considering same FR filter I am considering. So y of n I am having. Y of n is equal to a into x of n plus b into x of n minus 1 plus c into x of n minus 2 I am considering. Now is it clear? First I am developing the equation, followed by I am developing the circuit. See clear? Because once you have a equation circuit hardware, you may optimally utilize. See, optimally bring the hardware. See clear? That is the idea. So here because of 3-level parallel processing, n is replaced by 3k. So I am replacing with 3k. Y of 3k is equal to, just n is representation only I am varying, that's all. N is represented by 3k, that's all. A into x of 3k plus b into x of 3k minus 1 plus into x of 3k minus 2. This is for the first hardware. Second hardware, it is 3k plus n plus 1, 3k plus 1. If y of 3k plus 1, then a will be, because I should not change the IO mapping, a will be a into x of 3k plus 1. See clear? Because here if the x of 3k means a into x of 3k, then previous sample previous to this sample. Then x of 3k plus 1 means here also it is x of 3k plus 1. Then previous to this x of 3k, previous this one x of 3k minus 1. See clear? I am not violating the IO characteristics. Then 3 input we may consider. That's why y of 3k plus 2 I am writing. That's why a into x of 3k plus 2, b into x of 3k plus 1, c into x of 3k. See clear? And here I am not reducing the clock period. See clear? Clock not reducing, but I per clock period I am getting 3 outputs I am getting. That's why, see clear? TCLK is reduced by 1 by L. So if the direct form, we consider that we use direct form 1, then here it is, we consider direct form 1, then Tm plus 2Ta, that is the operating frequency. By applying 3-level processing, that is reduced, the clock reduced to 1 by 3. See clear? Clock will reduced by 1 by 3. See clear? And the sample speed is increased by thrice, that's all. For understanding. Now we arrived at the equation. Now we develop the circuit. For implementing this equation, we are bringing the circuit. That's all. And here, this is that is y into here. And one more point to be noted here is that here I am going to use delay elements. I am going to use, and here the clock period I am not changing. In parallel processing, clock period I am not changing. So every registered, every sample registers are going to work at clock period. If clock period is 12, that is 12 nanosecond, I am not going to change. In the pipelining, I am reducing the clock period. But here I am not reducing the clock period. The circuits are replicated. That's all. So same clock period I am using. That's why if I use a latch, see clear? So latch is going to operate on the clock period. So how much delay it is? If I use 12 nanosecond clock period, how much delay it is going to give? 12 nanosecond delay only it is going to give. But every 12 nanosecond, is it clear? I am going to get 3 output. That's why effective sample period is reduced by 3. 4 nanosecond sample I am going to get. So here sample speed is 4 nanosecond, but clock period is 12 nanosecond. That's why, see clear, in pipelining, see clear, in pipelining, always T clock is equal to T sample. Clear, but in parallel processing, T clock is not equal to T sample. T clock is equal to 1 divided by L into T sample. See, 1 divided by L into T sample, that we told here. 1 by 3 into Tm plus 2Ta, that is sample speed. Clock speed we are not operating, we are not changing. See, that is the idea. And these registers are operating by clock period. See, clear? And we are considering every 12 nanosecond, we are considering 3 samples we are considering. That's why it is also called parallel processing, also called block processing. If L is equal to 3, then it is called a 3-level parallel processing or 3-level block processing. It is also called 3-level block processing. Why I am saying block processing is that this registers, see clear, these registers are introducing block delay because it operated by 12. It is not operated by sample, it is operated by clock period. That is introducing block delay, not sample delay. That is called block processing, it is called. So samples I am going to take every 3 nanosecond, I am going to take the sample. But every 3 nanosecond I am going to take, sorry, 4 nanosecond here. Every 4 nanosecond I am taking sample, but every 4 nanosecond I am considering 3 samples. I am considering. See clear? That's why the circuit here is x of k, x of 3k plus 1, 3k plus 2, 3 samples I am considering at 12 nanosecond. And if the source is giving, sample by sample if it is giving, then you need to use serial to parallel converter, you need to use. And here your parallel processing system, MIMO multi-input output system is available here. So you take here samples are coming serially and you do serial to parallel converter. If it is 3 samples, then 3 samples are available at a time. Take clear. This sample may come at 3 nanosecond. But here this sample has to come at 3 nanosecond, but you by through serial to parallel converter you are keeping all the, here it is 4, if it is 3, it is coming at 4 nanosecond, and 3 samples you are keeping here for 12 nanosecond. Then again, see clear, again next 12 nanosecond you take other 3 samples. See clear, one by one you take, it is converted to parallel, and you keep available all the 3 sample another 12 nanosecond, like that. That's why it has to do. Then same way here you need to do parallel serial converter because it is going to give multi output. If you want to convert, then you need to use a parallel serial converter to give. So the sample speed, if you see, it is that is, if you follow level 3, then it is with respect to clock period, it is divided by 3. Here also it is divided by 3. But this is going to operate with respect to clock period. Are understanding? That's why in this structure, the delay are operated by 3 sample delay. See clear? So x of 3k, because x of 3k at 12 nanosecond, I am keeping x of 3k, 3k plus 1, 3k plus 2 I am keeping. Next is 12 nanosecond, what I am going to keep here? Here x of 3k plus 3 plus 4 plus 5 I am going to keep. Because already x of 3k plus 1 is considered. I need not consider again. That's why 3 samples I am considering. X of 3k, 3k plus 1, 3k plus 2 for 12 nanosecond. Second set of 12 nanosecond, I am giving x of 3k plus 3, 4, 5. Like that, 3 sample I am considering. Every 12 nanosecond, sample delay is reduced by 4 nanosecond. See clear? Thrice it is reduced. So here, first sample what I am keeping? 3k plus 2. Second sample what I am keeping? I am keeping 3k plus 5 only I am keeping. That's why if it is 3k plus 2 here, what was the previous sample? 3 sample, is it clear? Delay, ahead. That's why it is 3k minus 1. Here, if it is 3k minus 2, see clear? If it is 3k plus 1, what is the 3 sample? X of 3k plus 1, x of 3k, 3k minus 1, 3K minus 2. 3K minus 2 is available here. That's why the registers are introducing block delay, we may say, because those are operated by clock period, not the sample period. See clear? That it is also called a block processing system. Now with that you see the architecture. This is the architecture for, say clear, 3-level parallel processing with respect to equation. Instead of completely replicating the hardware, with respect to equation, if you develop, number of register will reduce. See clear? So because here if you see, totally I used 2 registers only. But if you take one single filter itself, is taking delay element, 2 set of delay elements. I supposed to 6 set of delay elements, but I solve with 2 set of delay elements. That's why you develop the equation. For the equation, you develop the architecture. It will be very convenient. Now let us see whether we are violating. Here if you see y of 3k, what I am taking, a into x of 3k to be done. X of 3k I am taking, that is given here, a into x of 3k I am taking. Then b if I take b into x of 3k minus 1. So here 3k minus 1 is available, I am giving to b. So b into 3k minus 1 I am doing. Then here 3k minus 2 I am taking, so c into 3k minus 2 I am doing. So that I am taking to get the output y of 3k. Understanding? Y of 3k I am getting. 3k plus 1 if you see. So a I supposed to get 3k plus 1. So a if you see, this is a coefficient. So here I am getting 3k plus 1 is given. Is clear? And the b 3k minus 1 to be given. Is it clear? B if you see, b 3k. Here 3k plus 1 it is 3k. So b I am giving 3k I am giving. Then c 3k minus 1 to be given. So 3k minus 1 is given to c. But I am getting the correct output y of 3k plus 1. Y of 3k plus nothing but a into x of 3k plus 2 plus b into x of 3k plus 1 plus c into x of 3k. That I am doing here. C into x of 3k I am doing. Then b into, see clear, 3k, see clear, b into 3k plus 1 I am doing. A into 3k plus 2 I am doing. By that I am getting y of 3. So I have not changed input output mapping, but I replicated the hardware, not only on the multiplier adders, not the delay elements. By the way, the effective sample period is reduced to 4 nanoseconds instead of 12 nanoseconds. Or understanding? Is clear or not? So this is the approach of parallel processing to increase the speed. For understanding? Okay, but when you give parallel sample, if source is giving serial, you need to convert parallel. That is to be done. Okay. Hello? What time am I supposed to stop? Hello? What time am I supposed to stop? Hello? What time am I supposed to stop?
ये पूछना चाह रही थी भाई, अगर सपोज करिए इसे बहुत मतलब बहुत अच्छी बात बताई आपने.
I don't think any organizer will be.
Sir, can you hear me, sir?
I think at what time am I supposed to stop?
10 minutes, 10 minutes.
10 more minutes, sir. You can take another 10 more minutes, sir.
Okay. With that, I will take another 10 more minutes. With that, I will stop.
Thank you, sir. Thank you, sir.
Now, okay. Now we move on to briefly. I am telling about how pipelining, parallel processing are reducing the power. I will tell you. Okay. For that, we are going to use two formulas. We are going to use. One is these are the first level approximation. That's all. So one is the propagation delay, another one is power consumption. For a CMOS circuit, we are discussing. For a CMOS circuit, propagation delay. So I told the critical path delay like that. How we are calculating the path delay? We are calculating. This is the first approximate formula to calculate the path delay. Okay. So A path delay is nothing but C charge. Capacitance available, total capacitance available, the capacitance available in that path. C charge. V naught is the supply voltage. V naught divided by K is the parameter. It depends on the W by L ratio, mu, other parameter. K is a constant. K into V naught minus Vt is the threshold voltage. V naught minus Vt the whole square. So this is the formula to be used to calculate the propagation delay of the path. Clear? Now what is the total power? What is the formula to be used to calculate total power consumption of a CMOS circuit? This is equal to C total. Total means here we are considering only the capacity available in the path. In power consumption, we are calculating total power, total capacitance available in the circuit. Calculating. So C total into supply voltage V naught squared into F. Supply is, we are considering, we are giving a supply voltage of V naught. So C V naught squared F, that is the formula. C is C total. Understanding? And for a sequence circuit, before applying pipelining parallel processing, circuit is sequential circuit. So we are representing sequential filter. That is nothing but, instead of P sequential, we are representing the power consumption of a sequential 3-tap filter. P sequence equal to C total into V naught squared F, we are saying. And T sequential, that is the propagation delay of a sequential filter, a path available, to be calculated by C charge V naught by K into V naught minus Vt square. And the frequency is nothing but 1 by T, generally clock period, 1 over the clock period is the frequency, 1 by, because this is the propagation delay. You take the propagation delay of the critical path, then 1 over that path delay is going to give frequency. That's why this T sequence you consider the longest path delay period. Clear? Longest path delay period. So 1 by T sequential is equal to the frequency. Now let us see. Now, see clear? Now you consider the filter, that is 3-tap filter. 3-tap filter, the critical path delay. See clear? For a direct form one, we discussed that Tm plus 2Ta. That is the critical path delay. See clear? That is. So if Tm plus 2Ta is equal to 4 plus, if multiplier having 2 delay, see clear? And multiplier having 4 nanosecond, adder having 2, then it is 8 nanosecond. So the critical path delay of that circuit is 8 nanosecond. Or understand, 8 nanosecond. So the critical path is available. The critical path is available, 1 multiplier, 2 adder. That path I am considering here. This is the critical path. Is it clear? This is representing the critical path, which is having for a filter 1 multiplier plus 2 adder if it is a 3-tap filter. See clear? And this is operated by 8 nanosecond. See clear? Or understanding? Assumption. Assumption, we are, that is not assumption. This line, you assumed that it is representing in a 3-tap filter, it is representing 1 multiplier 2 adder critical path delay you consider. See clear? This path, even though it is drawing a straight line, it is considered to be in a 3-tap filter 1 multiplier 2 adder path it is. And it is operated by T sequential 8 nanosecond. And the circuit is operated by a voltage of V naught. I given the supply voltage of V naught you consider. See clear? Are all clear? Now, when I do pipelining, what I am doing is I am cutting the critical path. By introducing pipeline resistors, I am cutting the critical path. So this circuit, you assume that I have done 3-level pipelining you consider. Then if I do 3-level pipeline, what I am doing is that I am making cut in the critical path. The critical path is divided into 3. I made 2 cut in the critical path. By the way, the path is divided by 3. Divided by 3, the path is. If it is 8 nanosecond, I divided into, see clear, equally. See clear? That is 2 something, 2.6, 2 point like that. I have divided, you consider. It is divided. Now, once you want to attempt, see clear, once you want to attempt lower power, then you are not allowed to increase the frequency. Either one could be obtained. Either one could be obtained. See clear? That's why even previously I was using t is equal 8 nanosecond to operate this path. The clock period is equal t sequential used to operate this path. Because of this path delay, I got 8 nanosecond. Now, this circuit after pipelining also, if I attempted to lower the power, I am operating the circuit again 8 nanosecond. I am not allowed to either one advantage only you may get. You cannot get both the advantages. So this also I am operating 8 nanosecond. See clear, clock period. Now if you see the 8 nanosecond clock period is going to, is it clear? Here the chi charges, here it is like this. Now the chi charge for this path is only divided by 3. So our understanding now, the clock period used to charge only 1/3 of the previous capacity is going to charge. That's why you need not use the same supply voltage for this one. The supply voltage could be reduced. Understanding? Because I am not reducing the clock period. Same 8 nanosecond clock period I am using to charge 1/3 of the capacitance compared to the previous 1/3. Previously, I was using 8 nanosecond to charge this much capacitance with a supply voltage of V0. Now, is it clear? Now, I am going to use again 8 nanosecond, but I am going to use only this much charge. 1/3 of the charge, chi charge I am going to use. By the way, I need not use V0 supply. I can use beta V0 supply voltage. I can use beta V0 supply voltage. With this concept, you apply in the equation, you may reduce the power. Now I am calculating, previously we told P sequence equal to C total V0 squared F I told. Now you calculate for this, you consider this filter. It is pipelined by 3 level. See clear? For this filter, if you calculate, for this one, conceptual wise, this one if you consider, then the total delay is equal to, see capacitance I am not changed. Total capacitance is still there. See clear? Still there. But voltage I have changed. V0 to beta V0. So V0 is changed to beta squared V0 squared, and frequency, same frequency I am operating. Same frequency I am operating. That's why F I am maintaining. That's why this is nothing but C total V0 squared F, you know that is P sequential. Here beta squared is additional. So beta squared P sequential, that is the P total power of pipeline circuit. And here V0, I told this beta V0 is not the increased voltage. Because the capacitance has reduced. I am maintaining with the same clock period. See clear? I am maintaining to charge. See clear? I am maintaining charge 1/3 of the capacitance. That's why supply voltage could be reduced. That's why what is the beta value? That beta is a positive constant having a value between 0 and 1. See clear? By the way, the power is reduced. Beta is between 0, beta is 0.5, power reduced by half. Or understanding, if beta is here, the voltage reduced by half. Beta is 0.666. Then the power is reduced by 1, the voltage is reduced by 1/3. Understanding? That's why here to operate this circuit, which is pipeline by 3 level, I need not use same, I can use reduced supply voltage that I am representing by beta. So beta is a positive constant having a value between 0 and 1. That's why beta squared means what? It is a fractional number. See clear? So it could be, see clear, power is reduced for pipelining compared to, say, if it is 0.5, then 0.5 squared times it is reduced. How much reduced means? P pipelining divided by P sequential. Beta squared time it is reduced. If beta is equal to 0.5, voltage reduced by half. Then 0.5 squared, 0.25, the power is reduced by 1/4. Understanding? Understanding? So by the way, if you are not ready to increase the speed, then you may bring speed advantage, power low. We may bring lower power by reducing the supply voltage. See clear? And propagation delay we are calculating because we want to find out the value for beta. That's why this is used. So T sequential is equal to, already we know the formula, C charge V0 is the formula. But T pipelining, C charge is reduced. If m is equal to 3 by 3. If it is pipeline by m level, C charge by m. If it is here, m is equal to 3. That's why 3 level it is reduced, I told. If you consider m level pipelining, then C charge reduced by m level. So C charge by m. So in order to do C charge by m, I need not use. I am maintaining same clock period, but I need not reduce. See clear? I need not use same voltage, reduce the voltage. That's why it is replaced by beta V naught. Here also V naught is replaced by beta V naught. Now if you maintain T is equal to T pipelining, then this, if you keep these two left hand side are equal, then you may equate these two right hand side. By the way, you end up with the quadratic equation. M into beta V naught minus beta the whole square is equal to beta and V naught minus beta the whole square. Once you equate these two, you will get this equation. Now, if you see M level pipelining, we know V naught, Vt, we know. By the way, you can find out beta. Once you find out beta, you can find out beta squared is the reduction. You can find out the power reduction. Supply voltage also you may find out beta into V naught, that is supply voltage. If beta you obtain 0.5, if original supply voltage is 5 volt, then the pipeline supply voltage is, say clear, 2.5 volt, and the power reduction is, say clear, that is 5 volt means 0.5 means 0.5 volt. That voltage is 2.5 volt, and the power is reduced by that is it clear, 1/4 it is reduced for understanding. Okay, with that I am completing. Say clear. So other things you refer the book. Say clear how parallel processing, because it takes long time. Say clear. And example, I think I am referring, all of I am referring Parhi book, VLSI DSP by Parhi, Keshav Parhi book. It is available in net itself. Lecture notes, all those things available in net. All of you refer. Any doubts, you send a mail to me. See, I think you know my mail ID. Refer the website. If any doubts, you are allowed to send a mail. I am ready to clear your doubts. See, clear? Okay. Any doubts till now? What I taught? Any doubts? Any doubts, dear participants? Any doubts? Hello? Any doubt? Hello? Any doubt?
Participants, if you have any queries, you can unmute and you can ask, or you can post it in the chat box.
Okay, then if no doubts, I am with that I am concluding my session. But you are allowed to interact with me. You are allowed to interact with me. I think my duty is whatever I told, it has to reach you. Say clear, I am ready to clear a doubt. Say clear, anytime you discuss with me. Thank you to all. Thank you.
Sir, thank you for your session, sir. It was a really wonderful session. Well explained, sir. Each and every concepts we have given a clear idea about each and every concept. On behalf of IIIT Management, Department of Electronics and Communication Engineering, and Department of Computer Science Engineering, we thank you wholeheartedly, sir. Thank you, sir.
Okay, thank you. Okay, I am leaving. The meeting.
Thank you, sir. Okay, sir.
Okay.
Participants are requested to fill the attendance form posted in the chat box. Next session will begin by 11:50 a.m.